Good. Thank you. Hello, everyone. My name is Anastasia Andreevska. I work at NCS at RISE, and today we are going to discuss why EULA language is suitable for high-performance data analytics, some motivations to this, and we will ask partially questions why EULA and how does it perform in comparison to other languages in terms of speed and efficiency for this specific subtask high-performance data analytics, and what are the key features of Julia that are beneficial for HPDA. So Julia becoming this language more and more popular, especially for supercomputers, even quantum computers, because it has some advantages. And why we would use EULA for HPDA? Because usually high-performance data analytics requires that type of programming language that can handle large datasets, perform complex computations efficiently, and also scale on high-performance computing systems. And Julia, in its core, in its design philosophy, it's trying to combine the best of both worlds, like speed of compiled languages like C or Fortran, and also easy to use languages like Python. And we can imagine this as a combination of C language, for example, and Python. And that's how you can get EULA and its best features. Also, EULA has the JIT, a just-in-time compilation. And this type of inference means that we can execute code as it speeds in regards to the speed, similarly like executes C or Fortran languages. Because you might know Python is very easy-looking language. It's a very big ecosystem. However, it's not compiled that efficiently in a similar manner as the C. So that is why programmers created an alternative, EULA, which combines both of the words. And that is why, primarily because of its execution manner, EULA is specifically well suited to perform large-scale computations, which are often required for HPDA. EULA has efficient memory management, which is useful for handling large datasets, and it also has support for parallel and distributed computing, making it capable of handling very large datasets, which is often crucial for high-performance data analytics, because one can work with terabytes of data. We also discussed some key features that are beneficial for HPDA of EULA language, and in particular, it could be multiple dispatch. This feature makes EULA code generic and composable, which is great for complex applications. Also, it has a feature of metaprogramming. So it means that EULA ability to treat code as data and vice versa. So it's useful when we utilize highly abstract code, which often is a requirement for HPDA. Also, EULA has seamless integration with other languages, so it's good for interoperability, and it's has great integration with Python, R languages, and even if there are some packages available in EULA, we will cover this, one can still easily because of this seamless integration to utilize existing libraries within Python ecosystem while benefiting from EULA performance. There are a lot of packages specifically for high-performance data analytics from EULA ecosystem. And they're developed more and more because EULA community increasing every day, and engineers write more and more packages, so it's becoming so popular as Python approximately these days, especially in realm of supercomputers. And there are many packages that are well suited for HPDA. For example, Dr. Watson is one of the first packages in EULA for these purposes, and it's designed to assist with scientific analytics of data, Sky machine learning package, different plotting and models packages that, for example, stats models is this package used for specifying and evaluating statistical models in ULE. To work with different dimensions of data and creating different arrays. There are dedicated packages for this, even for creating nearest neighbors, KD trees. For example, this package is useful for using methods for missing data in ULE, because sometimes if you have very big data set, you might have some missing data and you need to handle this within your analytics. So there are a lot of packages and they provide a wide range of functionalities that can be helpful for different high-performance data analytics tasks while utilizing ULE language. And you can then check these references for more details. However, as any other thing, it has some drawbacks. And in this section, we will introduce some of drawbacks of current ULE implementations and also workarounds, what we can do to help us with these drawbacks. For example, one of the important limitations is data size limitations. So ULE can handle large data sets, but if we're working with extremely large data sets, they might exceed your system's memory. And in that way, you might have some issues. However, within ULE, you have a built-in support for distributed computing. For example, you can split the data across multiple machines, and in that way, you will not exceed your system's memory. Also, I mentioned that there are a lot of packages and libraries within ULE, but not that much as within Python, because it's a new language and new ecosystem of programming language. But as I mentioned, there are already a lot of packages and they're being developed. And this ecosystem is being better and better. And the very cool feature of ULE, it has ULE interop that helps us to call functions from libraries in other languages. So it's good, we can use our common Python libraries, but interrupt it in ULE language. Another possible drawback you might encounter is performance tuning. So achieving optimal performance with ULE can require deep understanding of various aspects like type of stability and memory layout, and it could be challenging for beginners with this language or generally with programming on supercomputers. But there are, for example, one of the workarounds is to utilizing profiling tools available in ULE to understand and optimize the performance of your code. And here is a reference for more details. ULE provides several libraries, packages, constructs for parallel and distributed computing, but writing efficient parallel code can be still a complex task. However, there are some relevant packages like shared arrays and distributed package for specifically this task for parallel computing, distributed memory systems. So it's still possible. And there are a few challenges, they exist, but ULE community is very active and vibrant, and improvements are continuously being made, and this language evolving rapidly. And many of these challenges we discussed are likely to be addressed as this ecosystem matures. And meanwhile, there are maybe lack of some packages, you still have some workarounds, and it's very interoperable programming language. So it's really, you can utilize effectively ULE for your HPDA tasks. And there are some more resources that could be useful for you, specifically ULE for supercomputing packages, list of all relevant packages for supercomputing. There is even data science ULE community, sub-community, a website dedicated for data science problematics and how you can use EULA to help you with that. Data clustering, databases, and also, last but not least, EULA has a lot of different communities which are official, and they have Slack, Zulip, Discord, and you can join this community and ask colleagues how to best utilize this language if you have some issues or would like some inspiration. So it's very cool that there are many ways to connect with developers of this code. Thank you.
My name is Francesco. I'm in the CCS project and I work at RISE. What I will be talking about today is how to handle mainly two types of data. So we will start with tabular data, so what you will call pandas or R data frames in other languages. But it's basically, yes, data that can be represented as a table of observations, for example. And then later, after this, we will talk about more array type of data, so multidimensional tensors, matrices, vectors, and how we can do analysis on those. So regarding data frames specifically, we will look at, well, how to open and manipulate data frames, what we can do about missing data, and how to, merge data frames kind of like in SQL style. This will be optional, but we'll try to get around to it. And then how to do some simple manipulations. So we will take as an example some climate data in a couple of different cities, and yeah, we can do some type of spectral analysis around those. And we will try to give a short look, as well as the title says, into data formats and how we can store tabular data on disk. So yes, we will look at a Julian approach to manipulate and also visualize this data. So we will also look at a couple of plotting packages. And yes, the data frame, just to, so that we're all on the same page, is a two-dimensional table-like data structure. So you can think of it as a spreadsheet where each column is a variable and each row is, for example, an observation. And Julia provides a package to handle this type of data called dataframes.jl. And we will later also look at how to visualize it with packages such as plots and stat plots. But this is how data frame looks like. And we can do all the usual suspect operations. So filtering, sorting, stratifying or grouping data, and do some kind of aggregation with reduction operations. We will try to demystify all these terms in a few minutes. So again, the dataframes.jl is what you would call pandas or data.frame in R. It gives us quite a bit of functionality to clean the data, transform it, and pipeline into visualization. And it's probably, or for sure, the most popular choice for the manipulation of tabular data in Julia. So let's try to get some hands-on with this. We will play a bit today and also tomorrow with a dataset called Palmer Penguins, which is an open source dataset. And it is used to describe the features of 3 species of penguins that live on some islands. And the dataset contains some of their anatomical features, such as the beak length and width, their sex, weight, and some others. We will look at it in a second. The dataset is open source and is bundled in this package called Palmer Penguins. So we can start by looking at it directly. So I will open the Julia REPL here. and we can start looking into this. So in my case, I had already added I can show you how it will look like, but I've already added the Palmer Penguins package myself. Earlier, so it will tell me that there is not a lot to do. Sorry, my connection is a bit slow today. Yeah, but no changes because the package was already present, so nothing much to do. So since it's already there, I will just be able to use it. And I will have it now available. And we will use the dataframes package. So again, it was already added, so I can just go using dataframes. We will not probably do this very much, but it's possible, of course, to create data frames from scratch. There are several different ways that you can go about it. You can have, for example, different vectors, stitch them column by column. Most often you will read datasets from other sources, such as packages or CSV files or some API somewhere on the internet. But just for the sake of completeness, we can give a small example on how we can create ones from scratch. So in this case, I will create two vectors that will be the columns of the data frame. So I will give it some names. And this is a normal vector of strings, and I will give one of ages that in this case are also strings. You don't need to type along right now. There will be some exercises, but just so you know, if you want to test it yourself, there is a nice copy button that just lets you paste it into the repo afterwards. So we have our two columns, and I just create a data frame out of those. And the first, as you can see, I'm passing it a set of keys and values. So in this case, the key will be the name of the column, the title of the column in the data frame, and the value is the data that I'm actually passing to it. So this creates a nice 4x2 data frame. And you can pass it, you can do the same thing by passing it, for example, dictionaries or pairs of values. There's several constructors. This is all nice and good, but what you will do most often is to actually read from a data frame from some other source. So in this case, our data is contained in the package that offers a nice load method. So we just call it. And this will return a tabular structure. And this will look very ugly for now. And that's because the Palmer Penguins package uses in the backend a package called csv.jl. So the data is actually stored in a CSV file, and it will be returned as a series of rows. And this is nice, but it's not really usable for analysis purposes. So we can just convert it into a data frame. So this is one of the other ways that you can construct a data frame, just by turning a CSV file into a tabular structure. And let me do this. This is what you will see a lot more of. So we have a data frame where we have 344 observations and 7 variables, where each variable is a column. So the species, the island where it was observed, bill length and bill depth, that's what I called big before. Somewhere there is also sex and weight and the year. We can look at the first 5 columns, for example, sorry, the first 5 rows. And you can see already that some of this contains some missing values. So it's a quite common, probably, situation in which you have a tabular data structure and some of the values are missing. In Julia, there is a specific data type for this that is missing. And you can see that also from the type of column, this float64 with a question mark is telling me that all the values here are floating point numbers, but there can also be some missing. Whereas for species and island, we don't have any missing values. It's just a normal string without question mark in the end. So that's a way, of knowing if you have missing values. We will look at this mainly in an episode tomorrow. Once the data is read, we can also, after we do our manipulations, or if we want to just convert it, it can be re-exported in many common formats that are used in data science, such as CSV, JSON, Parquet, or Feather, that are very common in machine learning applications. I will not show every single package. There is an overview of data formats that can be used in different use cases that we developed for another course about Python. But apart from a couple of these formats, namely Pickle and MPI, most of the formats are also interoperable with Julia. So this can serve to use a nice guide of which format to choose when you're trying to work with data for analytics. We selected 3 of them here. So CSV, well, it's quite straightforward. So comma separated values, just dumped in an ASCII format. So it's actually human readable. JSON is also used for in the web application world mainly. So it's a way to exchange messages between services. It is also human readable, maybe not the best choice for numerical data, but it's also a way, and you can try to use this snippet to dump files into JSON. Parquet is commonly used for machine learning purposes. It has some nice features such as being able to load lazily. So if your dataset doesn't fit in memory, you can still load parts of it as you need, and it works very well for parallel input and output. And yes, I'm not going to show these snippets, but you can try them yourself, and just to have a feeling for the fact that you can talk to the outside world also using Julia. What I will want to look at a bit more is just looking at the dataset and inspecting it. If you come from the Matlab or Python world, some of these operations will look very familiar. So we can do some slicing, for example. So with this, we take the first row and the first 3 columns of the dataset. So yeah, row number 1 and columns 1 to 3. Julia, as for the most part, well, for actually always, indices of arrays starting from 1 if you don't tell it otherwise. So in this case, 1 means the first, but would be 0, in Python or C. You can refer to columns not only by number, but also by name. So in this case, we're doing something similar to Python Matlab for the rows. So we're taking rows from 1 to 100 with steps of 20. So this can be a kind of a false friend if you're coming from Python, because in Python you will have start, stop, and step, whereas in Julia it's start, step, and stop. And we can refer to the column by its name. So we just subset take the island column from this. And if you're not familiar with this column syntax, that's what it's called, that symbol in Julia. So it's a way I could do this as easily as enclosing this in double quotes. It means more or less the same, but this is a way to refer to the string representation of this column. I can also use a dot syntax, like data frames in dplyr or also in pandas. So this is the same, as saying this. Just a bit quicker. When we want to extract whole columns, we have two ways of going about it. One is this one that I just showed you, where we use the colon. This makes actually a copy of the column. What do you have here? Sex and body mass in grams. So this will actually create a copy of these two columns. If you want to access the column directly, what it will be called a view on it without actually making a copy, then we replace the column that we had with an exclamation mark, build length. Oops, millimeters. And yeah, so this can be used to do, for example, in-place replacement in a data frame, because we're not actually copying it, but really taking the data directly from the source. And yeah, it will work exactly the same, for example, if we were looking at two columns in a row. And we can do, of course, some general commands to get the shape of the data set. So we get the size, so 344 observation of 7 variables, number of columns, number of rows. We can look at the there is a unique command that you can use to find, for example, the number of the different unique species in a data set. So in this case, we have 3. And much like in pandas, we can use the scribe function to get the statistics, overall statistics of the data frame. So this will compute for each one of the columns some things like mean, minimum, median, maximum, number of missing values. This is just we're flowing out. Of course, some things are not defined. So, for example, for strings like species and island, we don't have, we can't do the mean of strings, of course. But for others, we can. And you can see also that when we have missing values, the mean is actually a union type. That is, this is telling us that it can be either a float or a missing value. And that's because, of course, if you don't tell it otherwise, it doesn't know how to take the mean of a missing value. To remove missing values, we can use the drop missing function. And we have two variants, like in many other Julia functions. So we have the version with exclamation mark in the end and the one without. The difference between the two is that the one with exclamation mark does it in place. So we can do drop missing df. And this will remove all the missing values. So you can see that the question marks here have disappeared. If we use the version without the exclamation mark, this will make a copy of the data frame without the missing values. So in one case, we do it in place, and in the other case, we do it by making a copy. We can also use another syntax with the function coalesce. But in general, yes, this is how you can remove missing values. You can also use a package called interpolations to, rather than dropping all the missing data, interpolating it from the data that you already have available. So now from my data set, I've dropped them. So we'll just recreate it from the beginning. Palmer penguins. So I will have my missing data again. And I can use a package called, as I was saying, interpolation to actually recreate the missing data. So we can go, for example, in the following way. We use a mask, is called, to find all the missing data. So for example, in the bit length column, this will return basically a series of bits that are 1 where I have a missing data in this column and 0 otherwise. And then I can construct a simple linear interpolator to do it. So I use this will create an interpolation object that will take the bill length column, and I will just take the points where our data is actually missing. And I can use, for example, a B-spline interpolator. So this created an interpolation object. And now that I have, you can see that I only have floats here. So my data has actually been interpolated well, or has been interpolated. Then I can replace the column with the data that I just created. The dot syntax is quite similar to Matlab, if you're more familiar with that. So it means that I'm doing an element-wise operation. And I will use the interpolator to replace all the values given by my mask. So now if I look at the B length, the numbers that were missing have been replaced. The data type has not been changed, but we know now that everything that is inside here is numbers. There are some more bespoke packages to replace missing data. This is statistics, what would be called the imputation of the dataset. And there is a package called impute.jl that does it. There is a mice.jl that does it. And this can be used to impute both single columns or multiple ones. We can also do, we can go a bit quicker in this part, so I can leave some room for exercise. The data that we have here is in the so-called wide format, as opposed to long format or tidy format. Maybe you've come across this term before. So in this case, we can see that each row is a subject and each column is an observation. So we actually have, we have that each column is a variable, but not the opposite. So this is telling us that basically each row refers to one specimen. But very often for data analysis, we would prefer to have that each row is a single observation, and is that each column is a variable, at the same time each variable is a column. This will become maybe clearer once I show you how to swap between one and the other. So first of all, to distinguish all the specimens, I can create an ID column that is just, integer identifier. So now my data frame will have a column in the end that's just going to be shown here that is a number. And then I can use the stack function to create the long version of this. So what this will do is, in a second, create the long version of it. So we have a species, we have ID, and then here we have a variable column. I could have chosen to call it something else as well. That takes the name of a column in the previous dataset and the corresponding value. So in this case, we can see that we actually have for each row one observation, not one specimen. So this will correspond to many of these rows will correspond to one that we had earlier, but makes data wrangling and manipulation much easier. And to go back, we can use the unstack function. This kind of corresponds to the melt and pivot functions in pandas data frames. So we have variable and value. So if you're familiar, we know pandas way of doing things. This will correspond to melt and pivot. Lastly, we can look at split, apply, combine workflows. So very often we data analysis workflows include 3 steps that are grouping or stratifying a dataset based on some column. Then we apply some functional modification. For example, we can do the mean or the maximum, some kind of reduction operator on each group. And then we combine the results. And yeah, this is referred to as split, apply, combine. This in Julia is achieved with a group by function and a combine that does both the combination and applying some kind of function to it. So for example, we can group the dataset by species and island. So we have, several groups that are taken together by species and island. And then we can, for example, get the mean of each of these groups. So to do that, we combine this again. And then we tell it that for the body mass, we want to get the mean. So this is basically saying put back all these groups by reducing the body mass to the mean of each group. So, I need a statistics package to use the mean function that I imported. And then I can do this. And this gives me the mean of the body mass. So in some of them I had missing values, so I didn't try, but for the ones that I do have, it worked. So this is a very common workflow, and we get that, in this case I chose the mean, it could be the maximum, it can be any function that I like actually to combine. But this type of aggregation is very common. And in Julia, the 3 steps are actually usually combined into 2. So I do a group by first, and then the combine where I can pass it the reduction operator. We have an optional episode about, partly creating that we've seen. So there is nothing really new here. but how to merge. For this, we can use the join function. You can look at it maybe yourselves. This is kind of comes from relational databases, where you can join in different ways, different tables. But I would like to stop here actually, and I would rather go down here in the exercises part. And we have an exercise here about working with data frames, and try to redo kind of similar things to what we have been doing until now. So we have 2 CSV files in our repository for this course. The link will take you there, and you can download them. And we have a series of tasks here that you can try to do. So reading and play around with filtering and grouping data, computing statistics. We haven't looked into plotting yet, so you can skip the last 2 tasks for now. But it's a way for you to play yourselves with this type of manipulations. So I'm thinking that maybe we can stop here. Yes, welcome back. Before we move into algebra, I just wanted to mention a couple of things about plotting, but we can, take examples from the linear algebra part regarding plotting. I just want to introduce a couple of things. There are several packages for plotting. Probably the most famous one is plots.jl. That is kind of like a high-level API that lets us work with several different backends. GR is the default one. I can interface with Matplotlib from Python, and also from Plotly and Plotly JavaScript. So it's quite interesting because we write one code, and then just by changing the backend, we get the plot resulting from any of these backends. We also have statsplots that is now it sits together with plots.jl, but provides some specific recipes for statistical use cases, such as volume plots or bar plots. Gadfly is pretty much the ggplot2 version of the Julia version of ggplot2 from R. So it's based on the grammar graphics. Vigalite is very good for interactive graphics and is wrapping of the original Vigalite library. It's quite interesting, for example, for geographical data plotting. And Meki, that is probably the newest one among all this, but you can also interface with several backends. And it's quite interesting to use it with WebGL, for example, to have interactive web visualization, and you can good publication quality plotting, but it takes a bit longer to get around to how it works. And plotting is mainly done with this plot function, and we pass it the x and y as we do in most other plotting packages probably, and we can pass it a bunch of options such as labels and type of symbols, and we can add lines to the same plot by again using the exclamation mark version of it. And there are several things that we can do, like scatter plots or histogram plots. This is just to introduce it a bit. But now in the linear algebra part, I will show you a couple of examples on how we can plot data. So in this episode, we will go very quickly through the basics. So vectors and matrices in Julia, how they work and which operations we can do on them. And the main example that we will look at is how to do principal component analysis. That is something that very likely you will come across in data analysis workflows. So it's a way to reduce the dimensionality of the data in first instance. We can quickly go through the basics. So we can create ranges pretty much as we do in Python or Python. This is quite. There is one thing that is a bit different. That is, this is a lazy range. So this is like a promise of a range, so to say, which will only be actually associated when we call some kind of vector function around it. It's kind of like an iterator in Python. Like, it doesn't actually produce the data that it's supposed to produce until you call it. Indexing and slicing work pretty much the same as they do in Python or in Matlab. So if you have, for example, normal vector, we can get the first element by doing U1. We can do kind of the same slicing as we saw in dataframes. Matrices are declared in a very similar way. So we just interrupt rows by using a semicolon. And they can be also sliced in a similar way. We have the usual functions such as zeros and ones to create matrices and vectors of the right shape. And operations work also quite similar to other things that you may have come across. So if you get, for example, another vector, we can scale them. So this is, we can do like this. Can do scaling, just multiply by a constant. We can do a sum if they're the same size, yes. Sorry. So this is an element-wise sum. The same goes for subtraction. We can do powers, but we have to be careful because in Julia, if I do, for example, in this case, u squared, this does not exist because it will try to do the matrix power of this, which is not defined for an array of this shape. So if we want to do it element-wise, we have to prepend a dot, like we will do in Matlab. Same thing if we want to do element-wise product, we have to prepend a dot and any other higher function, basically. So a sign of this will not work, but if we want to get the sign of each function, of each element, sorry, then we use the dot notation. If we have a lot of these element-wise operations, we can use the dot macro. So we prepend at dot, and this will basically take care of, prepending a dot to each operation where it's needed. So if we have a lot of those, again, this should be used. Prepending using this will basically put a dot on any wherever it's needed in this expression. We can have the usual vector matrix operations, matrix multiplication and powers. And to transpose, we either use transpose of A or A prime. So the basic things, so to say, are quite similar to your usual, NumPy or R or Matlab. I want to move on to a more juicy example, maybe. So we can see how to do principal component analysis to reduce the dimensionality of data. So just so that we're on the same page, we need to know what eigenvectors and eigenvalues of a matrix are, since they're heavily used when we do PCA. So when we have a square matrix M, a vector U is a eigenvector of a square matrix with a certain eigenvalue lambda. If the matrix M can be turned if basically we can find a diagonal matrix that contains the eigenvalues, and u basically lambda times u gives us back m times u. So this is used for what is normally called diagonalization of a matrix. So basically lets us turn any matrix in any square matrix, if it's diagonalizable, into a diagonal matrix. So it's basically a way of finding a rotation function that gives us a diagonal matrix. So if we use the linear algebra package, we can define the matrix that we had before. And much like Matlab, we can use the eigenvex function that gives us the eigenvectors and the eigenvalues. Eigenvectors are usually, depending on implementation, are defined without the sign. So if you run this code yourself, in this case, each column in this matrix is an eigenvector, you might find your signs switched. This is not really a problem, but if you wonder why your results are different, this might be a reason. So eigenvectors are defined minus the sign. And well, why is this useful? It's useful because we can use diagonalization of a matrix to try to reduce the dimensionality of the data that we have. And this is normally called PCA, principal component analysis. So the gist of it is that by computing the eigenvectors and eigenvalues of a covariance matrix, we're basically finding the directions in which there is the largest variance. So basically, we're taking a number of vectors that, if we project the data on the space created by these vectors, we're getting the closest space in a least square sense to the original sample. This is all very abstract, but maybe it gets a bit easier if we do it manually. So to do it, we will use the iris dataset. That is quite a standard dataset used for benchmarking of data science application, and basically contains measurement from 3 different species of an iris plant that are setosa, versicolor, and virginica. And each one of them has 50 data points. And it's basically a big table where we have 4 measurements for each data point. So we have the sepal length and width, and the petal length and width. And much like the Palmer penguins, this is a open source, very widely used data set. And in this case, it is included in the R datasets package. And we can just use it or get it out in this form. So get datasets. This is just how the R datasets API works. While we download, oh, there it is. So we have 150 rows where we have 3 species. And for each one of them, we measure these 4 quantities. So as I was telling you before, PCA finds the best approximation of a data set in a lower, usually dimensional space. And the eigenvectors that we compute with the diagonalization operation are what we call the principal components that are ordered in terms of importance. So basically, to each eigenvector, if I show you what we had above, to each one of these columns, eigenvector number 1, 2, and 3, we have an associated eigenvalue that is -1, 1, and 16. And the eigenvalues tells me the relative importance of the corresponding eigenvector. So the bigger the eigenvalue means that the stronger or the bigger that direction is in the space defined by the eigenvectors. This is quite similar if you have a fluid mechanics background to POD, proper orthogonal decomposition. Actually, it's the same thing. The POD is a PCA applied to fluid mechanics data, if you're familiar with this. So the idea is that even though this data set is not very big, we can try to perform PCA on this data set and see if we can project it to a lower dimensional space. So in this case, we have 4 variables. That is not many, but just for the sake of illustration, we can try to reduce it to, for example, 2 or 3 dimensional space. So to start with, we can take the first 4 columns. So we exclude the species since it's a string. And we do it, in this case, by copying it. And we turn it into a matrix so that we can operate on it. And we keep also the labels, since we can use them later to distinguish between the different species. So initially, when we want to do PCA, we want to work on center data. Center in this case means subtracted the mean so that it's centered around 0. So we get the mean of all the columns. So you can see that I took the matrix that I had gotten up here, and I took the average of each column. So I have a 1/4 matrix. And then I can remove it from all the cells. Oh, I didn't get the dimension of this. There is 150. Then I can subtract it. So this operation that I did here, dot minus equal, is basically syntactic for this line here. So for each cell, I'm subtracting from X this quantity. Now that we have this, we need to compute the covariance matrix. And that's because we want to compute the covariance matrix. That's because the PCA is the diagonalization of the covariance matrix. So in this case, it's quite small already. We wouldn't really need to do dimensionality reduction. And then we get the eigenvectors and the eigenvalues. So again, you might see that your eigenvectors are, the columns are the opposite sign from what I got, but that doesn't really matter. What is more important in this case is that if we look at the eigenvalues, we can see that the first one is quite small, for example, compared to the last 3. So this is telling us that rather than carrying around the 4 columns that we had before, we can carry around 3 instead, and still recover a good percentage of the total variance that we had in the data set. And that's where the power of the PCA lies. In this case, it's not really a huge difference because we're reducing from 4 to 3. But imagine having a very high dimensional space and you can reduce it still to something like less than 10. That's a huge gain, and by preserving most of the variance that our data is expressing. This the base or the space that is defined by these eigenvectors is orthogonal and normalized. So if we get this, we get matrix that has ones here, and these are basically all zeros. And to actually look at the data or the reduced data, we have to project what we had on this lower dimensional space. And projecting in this case means just taking the dot product. And we take, as I showed you before, only the last 3 columns, because these are the 3 largest eigenvalues. So basically, the whole idea is that rather than a 150 by 4 matrix, now we have a 150 by 3. And again, in this case, it's not a huge gain, but if we had a data set with hundreds or thousands of columns and still get it down to 10, that's quite a big improvement. And now we can look at our data looks like. And for this, we can go back to plotting. So I can have my using plots package here. And we can first, group or subset the data that we have by species of plant. So the setosa is what we had before. And this is basically just a nice trick to get from this 150 by 3, get only the rows that correspond to the setosa. And now we do the same for the other 2. And the last one, there is the Virginica. Now, when it comes to plotting, we will mainly use the plot command. And in this case, we're defining a single plot object. We can also go and plot directly. So we have 3 principal components, which means that our data set is 3-dimensional. So we need a 3-dimensional plot to visualize it. And we do this by passing it the basically X, Y, and Z arrays. Then I'm using the plot function, but I would still like to have my data to be represented as a scatter plot. So I can pass it a flag that is series type and tell it that it's a scatter. This could be, for example, a histogram, could be anything else. In this case, we want a 3D scatter plot and a label. So I do this, and now hopefully a window should appear with my plot. So I have here the starting of this plot. Then I can do the same for the others. In this case, I would like to overwrite the original plot. So I add this, and it will end up on top. And then I will just copy paste the last one. And then I can, just add some labels. So every time I basically have a plot object already open, I can just use the exclamation mark version of the plot command to overwrite on it. And I give it the names of the principal components. We have some exercises here, if you don't have any questions. You can try to do this yourselves. This is very similar to what we just done, but instead of using a data set, we're starting from some artificial data generated from a normal distribution. And you can try to follow this tutorial. And yes, it will get to something quite similar, except that it's 2D instead of 3D, so it's a bit easier to look at. And it's a good exercise also on the plotting package. There are several options that we can pass to a plotting command, such as marker size and type of marker. If we want, for example, stars or other symbols, we can pass limits to the axis, line width and line color. Rather than going through the options, I think it's more interesting if you learn by doing, by looking at these examples. And we have some parts about sparse matrices. I'd rather skip it for now, but maybe I can just say a couple of words about sparse matrices. So then you just have a bit of time to do the exercises. You can do benchmarking in Julia by using the benchmark tools package. And I will just add it now. Sorry. Okay, so I can go using benchmark tools. And the idea behind this package is that, well, let's try to generate a matrix of 100 by 100 with just 10% of elements. There are not zero. Yeah. And we can use these two macros. One is called time, and the other is called btime. Time includes compilation time and garbage collection, so it's not really useful. Or it is useful for whole time, but not, if you really want to profile your code. More worthwhile is using the btime macro. That will basically run this code, this power operation a lot of times, and tell me the average number of allocations and how long it took for each time. So this, if you want to do performance optimization on your code, it would be really your bread and butter for a lot of time. So in this case, this power operation took 300 microseconds to execute, and he allocated 6 times. So a good way to benchmark your code, is to put strategic btime calls in different parts of the function to get an idea of how much each one of these takes. Yes, we have other extra exercises, but I would suggest to start from this PCA example, since it's quite similar to what we've been doing. And yes, it's also a good way of looking at plotting in Julia. And the material in the previous lesson, you can look at it if you want to learn, for example, more about the type of markers or colors that you can use. But in general, what you should know is covered here. So with this, should be in good time to have exercises and then also move to the linear regression episode in the next hour.
Okay, it is 11:15. Welcome back. Let's move on to the next episode about the linear regression or generally regression.
Thank you. Yes, I'm David, and I'll be talking about linear regression to start with today. We'll be talking about non-linear regression and neural networks and things like that a little bit later. So on Friday, I think it is. But today we start with the most basic case, so linear regression. And I have a couple of examples here to illustrate how to do this in Julia. I mean, the basic thing with linear regression is that we have some data and we want to model that with some function, excuse me. In this case, we take a linear model and we hope that there's a linear relationship in the data so that model will be good enough for us. And one way to do this in Julia, which I think is very convenient, is to use this GLM package. This is generalized linear models. We don't have to bother about the generalized part here because you can do just the normal linear regression in this package. And I have a little starting example here where we generate data synthetically and then we will fit a linear model to this and see how it goes. So here we take an x vector, which is our independent variable, just a range between 0 and 10. And then we take some linear function, say 5x plus 3.4. So that will be a line in the plane. And so this is a regression in one variable then. And so to make it a little bit more interesting, we take that same line and we add some noise to it. In this case, normally distributed noise. So that's the n here at around n. I'm here using the at macro to do vector operations. And then we can plot that line together with the noisy points around it. I can copy this to VS Code, which I'm using here, and just run it. And so we get this line. It has slope 5 and some intercept. It intersects the line here at 3.4. And we get some points bouncing around it. It's different every time I run it because the noise is random. We generated this data and now we want to fit a linear function to it. And so the way we can do this in Julia is with the GLM package and the fit function. So in general, what does it mean to kind of fit a model to data? Well, we'll use some kind of distance measure that what's the best line that fits the points. And in this case, we'll use the least squares distance. So we basically take the distance from the points to the line, we square that up and we sum up the entire thing. So that measures the distance from the line to the data. And if we take our same line, so we had a 5x plus 3.4, and we can form, so one way of doing this is that you form a data frame
where the columns are, on the one hand, your independent variable x, and the other one is your noisy points, in this case, y noisy. And then you can use this function fit. You tell it you want a linear model, and then you have to give a formula. And in this case, it's sort of what do you want to model based on what? And in this case, we want to model y as a function of x. You plug in your data frame. So we can try that, see what happens. Try it in VS Code. So we have our same line up there. Then we get some results, and it's you're going to get the coefficients, so the intercept, that's the constant term in the linear function, and the slope, which is the coefficient in front of Cx. And you also get some other information like the standard error, the sort of how sure the model is of this, viewing the coefficients themselves as random variables. And there's a t-test and a confidence interval. But we can see that if we look at this, it's the slope was fairly good. 0.1, it's supposed to be 5. But the intercept, the constant term, is not that close, actually. 2.7, it's supposed to be 3.4. And we can see that also here that the error is fairly large. But this is due to the noise. We can run it again, see what happens. Now it's 4.2, 3.7, so a little bit closer, but still. So there is a bit of uncertainty there. But the main thing is how to do linear regression. You can use fit and write a formula, or you can do like this, just LM, linear model, then the formula. So shorthand for this. So let's plot, here we have extracted the model, but we can plot the results to see what the line we found looked like. And for that, you can use, this part here is the same as before. And then we can use GLM predict. And that applies the model to the points used for fitting the data. So on the training points, if you want. And you plug in your model into that. Then you get the predictions of the model. And we can plot that together with the original line there. So let me copy that to the VS Code and see what it looks like. So you see that there are two lines here. There's one blue and one green. And they lie pretty close to one another. And then we have the points. So the green one is the predicted line, and the other one is the ground truth or original line. They lie pretty close to one another, so we can increase the noise a little bit to get a worse fit, maybe a little bit more. I take 10 times the normal distribution. Now we see that the points are pretty scattered around here. And also the lines are fairly far apart. But that's how you can use predict to evaluate your model. Now let's see what time it is. Yes. So I will go, we lost some minutes there, but I will keep going a little bit more and then we'll do exercises. So that's linear regression in one variable. So the question now is, how do you do multivariate regression? if you have several variables, so sort of several inputs and one output, basically. And it's very similar. So I have an example here where we're actually going to generate generate synthetic data, but we will generate the linear function that we draw data from randomly. So we'll take a linear function in 4 variables, so n is equal to 4. And then we're going to generate the coefficients of that linear function randomly. There are 5 of those. There's one constant term, and then there's one in front of every variable. So C are the coefficients, which we draw randomly. And then we're going to take some independent points, or X matrix, which is also drawn randomly. So the actual linear function looks like this. So we take the matrix product of the data matrix X with the coefficients from the second one to the last, and take the matrix product of those two. That's evaluating the linear function, plus C1, which is the constant term. And then again, we add some noise to it to make it a little bit more interesting. So we have while noisy. And the framework here is that you do the same thing. You can form a data frame. And in this time, we have 1, 2, 3, 4 columns for the X. So it's the 4 variables. And then we have our noisy outputs. And like in the univariate case, you can use LM, and then you need a formula, and you plug in your data frame. So it's just the formula that is a little bit different. Here you put all your variables. So CX1, CX2, plus CX3, plus CX4, plus 1 you can also put there, which is the constant term. That's sort of understood here. And then we print the model and also see the actual ground truth coefficients that we used. So let's see if we can illustrate multivariate linear regression. So I copy that code to this window, and we run it. It doesn't plot anything here. It's in several variables, but let's see. Maybe it's a little bit wrong here. So we get the formula, and then we get the same information as before. Now it's a bunch of coefficients that come out. See x1, 2, 3, 4, and the intercept, and the same type of statistical information about the solution. So and we also printed the coefficient. So these guys here are supposed to be the same as the coefficient column here: 0.08, 1.34, negative 0.23, and so on. So that seems quite accurate. There's not so much noise in this case. As we can see, I took 0.01 times the normal distribution there. So main point here, you do the same thing, but you put all your variables in the formula section here. So the last topic here before we do some exercises is linear models with basis functions. So this is a way that you can do, now we're approaching the generalized linear models, a way that you can do nonlinear modeling using linear regression. And if we just start with the nonlinear function to have something to test on. I took this polynomial here. I generate some dependent variable data from -66. And then we take this polynomial, which is a quintic, so degree 5, x to the 5th minus 34 times x to the 3rd, x cubed, plus 225x. And we add some noise to that, and we plot this curve together with the noisy points. So let's just run that in VS Code. So it looks like this. So it has 0 is over here, so it has a 1, 2, 3, 4, 5 roots. And the question is, so how can we model this nonlinear function using linear regression? Or more specifically, how can we do this in a convenient way in Julia? And the trick here is to use basis functions. And that's basically that you kind of guess that you can model your data with a certain function of a certain form. And polynomials are like this. They are, in principle, universal approximators like neural networks and so on, that they can mimic any continuous function as good as you might want, if the degree of the polynomial is high enough. So the degree is this, what was 5 in this case. And if you take a general polynomial, let's say of degree 5, which looks like this, ax to the 5th plus bx to the 4th and so on, with this ABC up to f being indeterminate, unknown. While this is non-linear in the x variable, it's linear in the a, b, c, and so on. So that's the trick, that when you plug in a point there, if you have a data pointer, you know what the value is supposed to be. That's part of your data. That would be linear in a, b, c, d, e, and f. So that puts a linear constraint or condition on your coefficients, and you can use linear regression to solve this. Of course, the degree here is not something that you know. I started with a quintic of degree 5, so I'm going to take degree 5, but you typically have to test your way forward to know what the degree should be for, if you have some arbitrary function. So if we look at this briefly, we have the same thing as before, our polynomial. And now we're back to one variable here, in a sense. And we can form a data frame which has just the x and the noisy points. And then to use linear regression with basis functions, you can do LM as before, and you plug in your data frame. But in the formula, you can actually evaluate various functions. So in this case, you can explicitly write cx to the 5, that's one of your basis functions, cx to the 4th, 3, 2, 1, and the constant term. So you can plug that into your formula and then use LM to do linear regression and find the coefficients in front of these that are fit the data the best in the least squared sense as before. So we can see what happens with that. I'll just plug that in. So it plots the same thing as before. And then we get this out, a little table with the coefficients. And we can see the powers of x here. So let's see, x to the 5th, 1. That's what we were supposed to have. And x to the 4th is small. That's correct. Negative 34 is also good. And then this one is relatively small. That's the quadratic term. And then we get something like 225. So that's pretty accurate, except for the intercept, which is negative 0.38. That's supposed to be 0. So you see also the standard error is fairly large. So this is quite unstable. Now it's a little bit smaller, but it can be larger, as we saw. So that's a nice way of doing it, and I think it's a convenient syntax because you can write anything here if you want to have cosine or sine or other functions and do linear regression on those. Okay, good. So we have some exercises here. You'll do linear regression with some real data set, small ones. And then there is also something about basis functions with trigonometric basis functions and examples like that. So what do we have? Is it 15 minutes for exercises? I did an interesting experiment here as we wrap up. I tried to, let's say we take a degree 6 polynomial, which instead of the 5, we fit a sextic degree 6 to that. There's the blue and the green, or the two. One is the predicted and the other one is the ground truth. If we try to fit, as we did before, degree 5 polynomial to that data, it goes very, very poorly. So the blue one is the original sextic with noisy points, and the green one is the best that it can do with degree 5. So it's pretty poor. But that can be interesting to elaborate a little bit as well.